started here. The talk is Ozone HIPS, Unbreakable Windows. If you guys have cell phones, can you either turn them off or put them on vibrate? Now, everyone, if you want, double check at least. That's always nice. This is Eugene. He's going to be giving the talk. Enjoy.
Thanks, John. Can everyone hear me? Yes. All right. So my name is Eugene, and I'm going to talk about Ozone HIPS, Unbreakable Windows. I apologize for the subject. It's a bit tongue-in-cheek, but I figured no one else would come. It's just going to be yet another Windows talk. So there were quite a few talks on Windows, especially in the zero-day attacks. So you probably know there is no such thing as unbreakable Windows. Even if your machine is Windows box is unplugged from the network, all you need really is just a USB drive or USB stick. Come up to it, and you get kernel 0. So I'm going to talk about Ozone HIPS, which is a system that I developed last year, which locks down Windows boxes, Windows 2000 and up. So what is HIPS? So HIPS is this new kid on the block. I guess it stands for a Host Intrusion Prevention System. So some of you might have heard of, it all started with IDS and network IDS, and then we have network IPS, and then we have host IPS. So what's a host IPS? Well, a host IPS is, it's basically any piece of software running on an end system on a server or your desktop, which protects the underlying system. So it's as easy as that. In enterprise deployments, HIPS would be an agent running on a machine, be it a server or desktop. You would have a centralized management console which collects the logs, which pushes out updates, stuff like that. So all the security enforcement is done from the endpoint, and management is usually done elsewhere, usually in some central place. So I'm only going to talk about the interesting stuff, which is the enforcement on the endpoint, none of the management talks. So we're going to talk about a variety of things that Ozone does. It does quite a few things, or it tries to do quite a few things at least. It tries to protect against various memory attacks, buffer overflows, format bugs, all that good stuff. It tries to protect processes themselves, the application, using sandboxing. We're going to talk about more about that. Protects the underlying system, so the Windows hardens the operating system. It protects itself, and we'll see why. And I'm going to show you a little demo at the end about how it all comes together. So since Ozone does quite a few things, let's try to understand what are we doing and why. So when Ozone was designed, when I designed Ozone, I tried to address most of the attack vectors. So from remote execution to local privilege escalation to hiding attacks, et cetera. So I try to think in generally, what are the attack vectors that are out there today, and how can we prevent them? So as probably most of you are familiar with, when an attacker tries to gain access to a remote system, and let's assume a service system in this case, and we're not concerned with emailing some executables to a clueless person. We talk about attacking a remote system. It's usually achieved by means of remote buffer overflow. So you have a system, you analyze what services are running on it, you find an exploit, you write an exploit, whatever, and you own a machine. So it can be a buffer overflow, a format bug, heap stack overflow, it doesn't really matter. So to address this particular attack vector, we have to protect against a variety of memory attacks. So it will be a buffer overflow protection, as well as some of the sandboxing can also help. So once someone owns your machine, or you own someone's machine, you would usually try to hide yourself. So you would clean the logs, you would Trojan the binaries, you would load kernel modules, you would do all kind of nasty things that will allow you to, first of all, to hide yourself, and then give yourself later access without trying to exploit the service again. So to do that, we lock down Windows, we disallow tampering with system resources, we disallow loading of unauthorized code in user land, kernel land, and all that good stuff. So let's start with stage one. Let's start with memory attacks. So the protection layer is responsible for guarding against a variety of attacks, which we classify as memory corruption attacks. And these include, buffer overflows, stack heap, format bugs, overriding function pointers, overriding anything that will essentially give you control in the end. So it can be even, it can be even some attack vectors we're not familiar with today, but if they rely on overwriting and doing something funny in memory and then transferring control, we should be able to stop those. So the memory corruption attacks, even though they're very different in terms of how they get exploited, they're quite similar in terms of how they actually work underneath. So first of all, you inject a malicious payload. So you send a very long string, or you send an integer, a very, very large integer, or you send a %n to a format, as a format string. So you inject the payload. That's one. Two, once you injected the payload, you want something to happen. Most likely, you want your code to run. So you need to transfer control to your payload. That's step two. There's nothing we can do to prevent payload injection, or there's very little we can do. We can't stop string copies from overwriting your buffers unless we want to instrument code. But without code instrumentation, we can't fix your bugs. The bug's always going to be there. So even though we can't fix the bugs, what we can try to is to stop those bugs from being exploitable. So how do we prevent, how do other people prevent bugs from being exploitable? There are a lot of solutions. Some of the more popular ones are on this slide. These are all software-based solutions. There's also some hardware stuff like NX, which can be bypassed with some of the techniques that are being bypassed, for example, writable page execution. If you saw my talk last year about, once again, hips, but then I was talking about breaking hips, then you saw a demo where about 15 lines of assembly code were used to bypass the writable page execution. The way this works is very, very similar to return into libc, where you set up a fake stack frame, and your hips basically doesn't realize that you're actually running code off a stack or a hip because the addresses look fine. The way this works is you would hook a bunch of APIs, or at least how these products work. You can do it other different ways. You would hook a bunch of APIs, and then you would check whether the APIs are running from a writable page. And a writable page can be a stack, it can be a heap. But it's probably not going to be text segment. So when you exploit a buffer overflow, for example, you inject into a writable page because you need to be able to write to memory. So you get injected into stack or into a heap. And so when you check where the code is executing from, if it's going to be a writable page, stack or heap, your process is going to get killed. Now, like I said, you can set up a fake stack frame that tells the intercept that you're not running from heap, you're running from elsewhere when you're not. And so it's pretty trivial to bypass. If you just came back from the NX talk, then you can use similar return into libc technique to bypass hardware-based attacks as well. So if you get a 64-bit Opteron and you enable this stuff and you go to bed happy, then maybe you shouldn't be. The other pretty popular solution, which is pretty good for what it tries to do, is a compiler-based solution. And these are StackGuard on Linux, Propolis, and OpenBSD, Visual Studio, and Windows. They all work in the same way, more or less. They set up some random number, canary, on stack. When they return in the function epilogue, that they make sure that the random number that's on stack is still the same random number. That is, it's not being overwritten. If it was, then you probably overwrote the return address, which is a bad thing. So these are not as easy to bypass as a writable page execution, but at the same time, they don't cover a lot of the attack vectors. They're good at stack overflows. They're not so good at heap or some format bugs. Finally, there's address-based randomization. There's PAX on Unix. There's Ozone on Windows. There's some other products that do this as well. So I'm going to talk a bit in more details about address-based randomization, which is what I implemented. So what's ASR or ASLR, as it's more commonly known? Well, the basic idea is you randomize the addresses in memory. So you hide where your code lives, where your stack lives, where your heap lives. And the reason for that is if you look at the typical exploit, you will realize that most of them have some built-in dependencies. And those dependencies are on static addresses. So if you change an address, the exploits stop working. It's as simple as that. The way this works in Windows, the majority of exploits, you would overwrite a stack. When you overwrite a stack, you usually corrupt some registers, and the registers would have the address address of your payload, so your buffer. So then you override the return address with an address of an instruction which will call that register, and that will transfer payload. That will transfer control to your payload. So that's the critical point. There is a static address in the majority of overflow exploits in Windows. So you look at Blaster, you look at Slammer, you look at all the big nasty worms, and there is a single address that's being used in those machines. And the reason why they've been so successful is because the majority of Windows boxes look very similar. The DLL is going to be loaded in the same place, on the same, across your entire server farm. The addresses do change between various service packs and hotfixes, but there are some addresses that are being used. If you look at, for example, at Metasploit, they found some addresses that are very common across multiple service packs. So you have a single address that works on every single Windows 2000 box. That's pretty powerful. I mean, you can write a worm that will work reliably on every single Windows 2000 machine in the world. And we know that works. If you look at Blaster, I mean, that took down a lot of Windows machines. And that's because they all look the same, absolutely the same. There's no diversity. So address space randomization solves that problem by randomizing addresses. So every single machine looks different. Your machine A has address A, the next one has X, Y, and Z. So when you try to run the same exploit, it's not going to work. Or rather, it's going to work in 1 in a million chance. So if you have 4 million machines, one of them will get owned. That's pretty good. So we randomize all the addresses that are used in exploits. Stack, heap addresses, where our libraries are loaded. Everything that can be used in an exploit, we randomize. And so, like I said, as the address space layout of each instance of an application is different, your exploits are not going to work. Or they're not going to work reliably, which is good enough. So here's an illustration. Basically, let's say a notepad. We start notepad once, and then we start notepad twice. And it can be the same machine, it could be different machines. But the point is, they all look different. If this was on a non-modified system, they look the same, absolutely the same. They'll have the same built-in address on every single machine. And Windows 2000 XP will look absolutely the same. But with address space randomization, they'll look different. And they'll look different enough for exploits to simply stop working. So the way I've implemented, there's some wrong information in the slide, which I'll correct. But the second heap randomization, this is very, very easy to do. I mean, it is so easy that I think it should be included in basically a stock operating system. It has no overhead. Literally, there is zero overhead at runtime or static, anything like that. It's free. And it doesn't provide actually 16-bit of it. I think it provides more like 30 bits. So that means that your stack can be in 2 to the 30 locations, which is about 1 billion different combinations, which is pretty good. Which means that now when you run the exploit and relies on an address of your stack, it's not going to work because your stack is going to be all over the place, and there's no way you can predict it. So that's the most important bit. When I talk about entropy, that's one of the ways that people attack address space randomization solutions. They try to predict where stuff is. So they try to predict, to brute force where stack is. There's been some papers published, for example, in Using Security last year, where I believe they attack packs because there's not enough entropy. They've been able to brute force address. They basically got lucky enough to get that one address. So with 30 bits of entropy, it's not that easy. I mean, you can run for hours. And when you try to own the intranet, it's simply not going to work. And the stack and heap randomization randomizes stack and heap application that does not break any applications at all. I mean, I have run dozens and dozens of different applications in my system, and I've never seen anything of them break. Because a sane Windows 32 application doesn't need to know where stack is or heap is. If you have a dependency on an address there, it's broken. So the DLL randomization is more important than stack and heap because the DLL addresses is what usually used in the exploits. So if you remember, I mentioned that you override your return address with the address of instruction that will call your register. Well, those addresses usually live in DLLs. It can be kernel 32.dll, or it can be NT.dll. It's going to be one of those system DLLs which don't change much across different Windows instances. So randomizing DLLs is essential. DLL randomization is a little bit more difficult to implement. The way I've done it, it has upfront CPU cost, which is the time to relocate the actual DLL. And there's some memory overhead because your DLLs are loaded in different places, you can't share virtual memory anymore, which is which is a loss. In terms of entropy, once again, it's about 30 bits, maybe 29. It's certainly not 14. So once again, your DLL can be all over the place. If you're familiar with the process layout on Windows, you get the first 2 gigabytes are for user land processing, and the next 2 gigabytes are for kernel. And the way it usually works in Windows, there is at the end of the user land 2 gigabytes, all of the DLLs usually get loaded there. Well, when I load DLLs in my system, that can get loaded anywhere in the 2 gigabyte space. So once again, you can't predict where that call EBX instruction is going to be. And DLL randomization is a little bit more intrusive, but it can be still pretty reliable. It might break certain applications, but in most of the cases, it works reliably enough. So what are some of the challenges doing SLR in Windows? Well, there are actually quite a few. I mean, first, of course, the fact that Windows is a closed source operating system. We don't have the source, and we have some documentation about how it works, but I guess Windows, Microsoft preferred for us not to know it. So simply implementing something as intrusive as randomizing the locations of stack and heap and DLLs on Windows is already, difficult enough because you don't know how things work. The only way you'll find out, you can disassemble the loader, you can disassemble the kernel, and that takes quite a bit of time. So I was stupid enough to do that, and I've spent a lot of time on very low-level code, just putting together a number of hacks that work together to provide the type of randomization that we're talking about. So for example, Windows Loaded doesn't allow you to randomize kernel 32 DLL. So Windows assumes that your kernel 32 DLL is going to be loaded at the same location for every single application. So when you try to rebase the thing, the loader will come back and say no. And the reason for that is because kernel 32 DLL string is embedded in the actual loader. So it's being treated specially. And the reason for that is pretty technical. Basically, when you call the create process API, it assumes that the process that it just created has the same layout. So it assumes that kernel 32 DLL is going to be loaded in the same place, which of course it's not for our systems. So not only did I have to trick the Windows loader to be able to rebase kernel 32 DLL, I also had to trick the create process API to load your application from the correct place. So there are multiple things that have to be done to be able to carry that out. And TDLL is another special DLL in the sense that it's loaded at boot time. It's loaded before a single user service is created, before most of the drivers are even loaded. And after it's loaded, it's mapped into every single process. And there's no way you can rebase that because it's already preloaded before the Windows even boots up. So runtime and TTL randomization is a lot harder. If you want to randomize, you have to do it before Windows is even loaded. So you have to do it at boot time. You can, of course, randomize DLLs statically. You can run rebase.exe and randomize DLLs. That will work. But if you want something at runtime, you have to do some tricks. One thing I should mention is that there are some products out there that do various virtual memory optimization. That's what they call it. And basically what they do is they rebase DLLs so that there are no collisions. And the reason for that is, like I said, when you load a DLL in a process, in two different processes, you only have one instance actually in memory. And it's being shared across two different process instances. So you save memory that way. So there are products out there who rebase DLLs, but the reason why they rebase them is to get, quote unquote, virtual memory optimization. They don't do it for security. But of course, when you rebase a DLL, you get the same idea. So you can take the products that are out there that do virtual memory optimization. You'll get the same result. You'll get random DLL. So that's one way to do it. We do it on runtime, which is slightly different and a lot more complicated. I'm not sure, which one is better. Not only that, but once again, there are more challenges on the way. So first of all, the Windows 32 compilers do not include relocation information for executables. So the reason why you can load a DLL at a different address is because Windows know where some of your addresses, some of the static addresses live, and so you can repatch them at runtime. The executables don't have this information because when a Windows loader loads an executable, it assumes that the address space is empty, which it is. When the exe is being mapped into the address space, there is nothing else that lives in the address space. So you know that you'll never have a collision. So you can always assume that you can load it there, and so you can drop the relocation information and make your binary smaller. DLLs, on the other hand, you can't make that assumption, even though you do have a base address. Base address is only used as optimization. It's not essential. You can load DLLs at different addresses all the time, but it's going to be slower. So executables, on the other hand, don't have this. So this means the text segments are not randomized, or they're not being randomized by Ozone today, which is an issue in the sense that if you find a COLI-BX instruction in your text segment, you can just replace that with, you can just use that and it'll still work, which is a problem. So what do we do about this? Well, we can try to force compilers to include relocation information, but since we're interested in protecting commercial products to which we don't have source code, that's not an option. We can try to relocate and rewrite binaries at runtime. That will certainly work, but it's very, very intrusive. So I'm not sure whether people are interested in going to the depth of doing that. And finally, the important point is that, yes, ASLR stops buffer overflows, but it doesn't, it might not be accepted for all applications, because what ASLR does, it prevents buffer overflows by turning them into denial of service. Because when you replace an address which is a COLI-BX with an address which actually doesn't point to anything, your application is going to crash. So, which is certainly better than getting a shell on a machine, but it still might be acceptable for some companies for some applications. Let's say you're Amazon.com, and you lose about $1 million of an hour downtime. You might be, you might make a decision where you would rather run your service and when you're owned, rather than running a service, rather than having a service down but not being owned, So that's something to think about. So as a conclusion for ASLR part, it's address space randomization randomizes the base addresses of various memory regions, such as stack, heap, DLLs. It doesn't provide 100% guarantee, but it does prevent most of the exploits because they rely on static addresses. Stack and heap randomization has no overhead, and it doesn't break any applications, so I didn't see why it can't be included in most of the stock operating systems. In fact, if you run Linux, I don't know what distributions, you get this already. OpenBSD provides this already. Windows doesn't yet, and I don't think the future versions do it either. But in terms of stack and heap randomization, I'm pretty sure when Microsoft can include it, and it'll still work. So are there any questions? Any questions about the ASLR stuff before we go into sandboxing? Yeah. The question is, can't you use a knob sled to increase the chances? The knob sled is used to. I mean, when you have 30 bits of entropy, your knob sled have to be 2 gigabytes for this to work. And of course, your heap is not 2 gigabytes. Your buffers are small, right? So at some point, you're going to run into a region which is, you possibly get killed. So you only have about, I don't know, 4K of data to play with before you run into memory which is write protected and you get killed. So, since we're talking about 30 bits of entropy, unless you can inject 2 gigabytes of knobs, it's probably not going to work. So we're safe. Yeah. 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 True. Well, in most of the way that those systems are implemented, yes, when you use systems that do virtual memory optimization, you get them to randomize it per machine, which is good enough because, when we're talking about protecting, let's say, 4 billion machines on the internet, as long as each machine is different, you're fine. If you have some malicious user in your machine, well, you're probably owned anyway, but it's not going to protect you when you're running a local exploit because you can find out what your address space looks like. But since we only care about the fact that we have diversity in our network, that our server farm looks different enough, our 100 servers don't have the same addresses, that's fine. But yeah. I'm sorry, say it again? How do those systems coexist with Windows file protection? They probably disable it. There's no other way because otherwise, of course, well, different systems work differently, right? Some of the systems actually, what they do, one of the systems that I know of, it rebases your DLL and it stores it in an alternative data stream. And so it modifies the Win32 loader. And so when you load it, it checks whether the alternative data stream exists, and it loads it straight from your binary, which is just a different a data stream, which still modifies the binary, but there are different ways to do it. The other system, the way it works is you would take a DLL, you rebase it, and you put it in a different directory, like a cache directory, and your Win32 loader then is hacked to load your DLLs from that directory. And this way you don't even modify the system binaries, which is a pretty good idea. So if you've screwed up and you reboot, then you can load from, you can load without any issues. So. That's a very good point. The question was, well, what happens when you allocate a heap, let's say, a megabyte before you run out of user land? And in this case, you're pretty much guaranteed the application is going to die, because if your heap, let's say, grows to a gigabyte, then you need to make sure that your heap is below 1 gigabyte mark. That's a very good point. So you can obviously control, stack doesn't usually go over 4 megabytes, so you can make sure that stack is can live there, but you can play some artificial binaries in, for example, where a heap is loaded. So you can push it down a little bit. So, but yeah, that's a good point. The question was, do you need all your DLLs needs to be loaded at page boundaries? Yeah, you need to preserve the alignment. So for example, when I randomize stack, I preserve the 8-byte boundary. And when you load DLLs, you cannot load them in the middle of something. They're always on a 4K boundary. So yeah, when you randomize, you actually, the reason why it's not 30 bits for DLLs, that's a good point. It's 30 bits minus the 4K, which is 12 bits, so you get about 18 bits. So yeah, you need to preserve alignment, otherwise software is not going to work. So let's move on to process protection. So, okay.
Have you quantified the impact of the memory overhead?
So the question was about the memory overhead. The memory overhead comes from the fact that when you load a DLL, the text segment is essentially, can be shared across multiple processes, right? So let's say you start on Notepad, and Notepad loads kernel 32 DLL. The kernel 32 DLL is not going to get loaded 10 times. Well, it is going to get loaded, but it's going to get mapped only once. So in memory, you only have one instance of your kernel 32 DLL, even though you have multiple processes running. So because text segment doesn't change in the executable, well, doesn't change most of the time, you can do that. But when you rebase your DLL, you relocate the stuff. So you have some hard-coded addresses in your DLLs, and you need to patch those. So you rewrite the text segment of a DLL. And because you rewrote the text segment to point to one set of addresses, the next process is not going to have the same set of addresses, so it's not shareable anymore. So when you have 10 notepads, you actually have 10 notepads loaded. 10 copies of kernel 32 DLL loaded. So you've just, if kernel 32 DLL is about 1 megabyte, you've just wasted 9 megabytes. Not wasted, but it's an overhead of 9 megabytes. So what you can do is you have to make sure, if you don't have the overhead, you have to make sure that all of your randomized rebased DLLs still have the same address. So that way you don't get the overhead, the memory overhead, or the CPU overhead. So it's possible to do it without this overhead. It's just a slightly different implementation. So let's talk about the process protection stuff. This is the sandbox, the part. So whilst the ASLR does prevent some of the attacks, we can't rely simply on SLR to stop all the attacks. In addition, there are other types of attacks that cannot be prevented simply by randomizing stuff. So the next layer, which sits on top of memory protection layer, is the process protection. And basically, the process protection is a sandbox which executes all processes in a sandbox. And what's a sandbox? A sandbox is a piece of software which mediates all accesses to system resources. So when your process tries to open a file, before it actually touches the operating system, the sandbox kicks in and verifies that you're allowed to touch the file. So sandbox enforces, my implementation of sandbox enforces all the rules from kernel mode. So it cannot be bypassed. So you can't, bypass the sandbox and hit the operating system directly. You always go through the sandbox first. So the sandbox always gets a chance to deny, access to a file, registry, or whatever. And the sandbox that I implemented mediates access to all system resources, and there are about 20 different types. And by system resources, I mean it can be a file, it can be a registry key, it can be a network connection, it can be a directory, it can be process execution. I'll show you some more examples. But pretty much anything that you can put a name on, you can control from a sandbox. So how's all this stuff defined? Well, there's a policy agent, and the policy agent parses and deals with those sandboxes, which are described by policy files. So a policy file is just a collection of rules specified in a text file. So each application gets a policy, which is just a collection of resources that are listed in that policy. So let me give you some examples of a policy. Well, the first rule, I mean, first of all, you can probably read this stuff and understand what it does without even me explaining anything. If you ever work with systrays, you can definitely read this. So this is pretty self-describing. The rule starts with a resource type, so a file or registry. Then it has some actions. So for example, you can read a file, you can write a file, you can execute a process, you can create a connection. So you define a resource and you define what are you trying to do with the resource, and then you specify an action. So deny an action, you can deny an action, you can log an action, stuff like that. You can also be a little bit more specific. So instead of just naming deny all driver loads, you can say, be more explicit and say, specify a file name or a driver you're talking about. So for example, the first rule says all file operations on a particular file name should be denied, okay? So the file name is a special file name, and it identifies a softice in a system. A softice is a kernel debugger in Windows, which I use for kernel code development. Unfortunately, some third-party software doesn't like softice being loaded because you can use softice to disassemble their code and find out how it works. So they check for softice on your system, and the way they check for softice is they check whether the driver for softice exists, which calls SIWVID. So if they can't find the device, they assume that it's not loaded, okay? So I run iTunes and Skype, which don't like softice, with softice on my system. So when iTunes loaded, my policies say deny access to a softice device. iTunes try to open it, it fails, it assumes it's not there and loads up. So if I want to now disassemble iTunes or Skype, I can do it. So the protection that those systems use are not very good. So you can do. So the next rule, let's move on. Let's look at the next rule. It basically says a registry read. So if you try to read a registry key which ends in secret, then quietly deny this without logging. So a star basically match the entire path. A single star is going to only match something between two slashes. The next rule basically says load all attempts to load a DLL. Pretty self-explanatory. The driver load deny will deny all attempts to load a kernel driver. Process execute rule states that if you try to execute a process which is called OK.exe, then allow it. You usually have to specify the entire path, but this is just an example. So if you run OK.exe, you're OK. It's allowed to go through. Similarly, if you try to connect a TCP connection to IP address 127.0.0.1, then allow it. So you can do that. Finally, you can say network all ask. This is going to basically act as a personal firewall. So if you use what's called Zone Labs, you can get this functionality with a single rule, which is pretty cool. You have different policy hierarchies. You can specify rules that apply to all users, all applications. Then you start getting more granular. You have policies that apply to a specific process. Then you go down one level. You have policies that apply to a specific user. So you can specify on multiple levels. Some rules can override each other, but you can create various policies which interact with each other in different ways. So there are also different policy types, and this is a logical concept. And if you ever worked with firewalls, then they'll look very similar. The policy types are deny all and allow all, which is pretty self-explanatory, right? If you ever configure a firewall, you say block all connections, but allow the following two to go through. Or you can say allow all connections to go through, except for the known bad IPs. So same thing here. You can say deny all access to a specific resource, except for the known good ones. That's a deny all policy. So if you, for example, know that your Outlook.exe is only supposed to execute a single process, and you say process execute name of that process, then permit, and then say process execute deny. So your Outlook will now be allowed to execute a single application. So if you try to run, Kornikova.exe.vbs, it will fail. On the other hand, if you know that Outlook's supposed to run all these different processes, but it's not supposed to run VBS scripts, or not supposed to run a single executable that you know is bad, you can do that as well. You can say process execute, bad.exe deny, everything else goes through. So it's up to you to decide which policy type you can create. So how do you go about creating those policies? Well, there are two different ways of doing it. You can do it manually, or you can do it automatically. So the manual process is, well, you open a notepad and you enter the rules. And it's okay for creating allowable policies because you know what you need to allow access to. So you know that bad.exe shouldn't be allowed to, but everything else is okay. On the other hand, if you try to create a policy for a complicated application, or you simply don't know what application does, then you obviously can't specify all the different resources because you simply don't know what they are. And so to simplify that process, I've developed, the Ozone comes with a little application which will monitor the application for you and then dump out all the resources in a policy format. So you run your application, you use it as you would normally, then you say stop training, it's called a training process, and it creates a policy for you. And so from there on, you can use this as a template for your process. So then you know what it's supposed to do. And that's done automatically. So what are some of the challenges with doing sandboxes in Windows? Well, the first one is host applications, such as service host and DLL host. Those are special processes which don't actually do any work, but they do the work on behalf of other processes. So for example, service host, which starts up a lot of services. And when you go into services menu in your Windows, there are about, I don't know, let's say 50 different types. Well, 25 of those run in context of service host. So your service host can run as alerter, it can run as a messenger, you could all these different things. And they all execute in a single service host.exe process address space. So when you create a policy, when you try to create a policy for service host.exe, you actually have to accommodate all these different resources which runs inside this, in that context, which is pretty difficult. So without actually knowing what instance of a service host it is, you can't actually do anything. You can't lock them down because they do so many things. Internet Explorer is very similar. I mean, the policy for Internet Explorer is protection all off. End of story. Internet Explorer can do everything. It can connect to every single website. It can read every single file in your systems. It's integrated so tightly that it's supposed to do everything. When you use Windows Update, it overrides your system binaries. It's all in the job spec for Internet Explorer. So protecting Internet Explorer is very, very difficult, or at least not with a deny-all policy. It must be allow-all, where you basically deny the bad stuff. Because Internet Explorer can just do too many things. Another one, I have a screenshot here, which shows the DLLs that are loaded inside of Acrobat.exe. So I was doing some work, and for some reason I was debugging Acrobat, and I was looking at the DLLs that are loaded inside of the process, and I was pretty surprised. I mean, can you guys name? Can you look at the screenshot and tell me what are the two things that are obviously wrong? What's this? Yes, Yahoo Messenger. So, like I said, it's Acrobat.exe, and it has at the bottom, if you look at it, it has two Yahoo Messenger DLLs loaded at it. I mean, what is that all about? Well, my guess is that Yahoo Messenger tries to figure out when you're idle. If you look at this idle.dll, so it hooks the process to find out what's going on in it, and it does this for pretty much, not for every process, but for most of them. So that's the type of complexity we're talking about in a Windows system. You have applications running inside of other applications. For example, I have an antivirus running in my machine, and I've noticed that antivirus actually, some of the code of antivirus run inside of my process. So when you run Acrobat.exe, you actually have code of antivirus code running inside of that code. So you have these code, coming from all the different places loaded up, and it's a jungle. You can say, on Unix, sandboxing works pretty well, right? So you set up systrace, you say your Mozilla is allowed to run from user bin Mozilla and allowed to read your home directory, and you run it and it works. On Windows, you do the same thing and you figure out that it doesn't work. And why? Oh, well, Yahoo Messenger failed to load and it screws it up. And then antivirus is trying to open a file and it screws it up. And then something else and then something else. It's just very, very complicated. Another thing to notice on the same slide is the order. Order is basically the number of DLLs. So if you look at the bottom, it's 100. So when you open an Acrobat.exe and you open a PDF, you read a PDF, you've just loaded 100 DLLs. Okay? So that's just to read a PDF file. I recently had to develop some code which is reading a CPU counter. I had to find out what was the load on my machine. And I've noticed that whenever I try to read for the first time the counter using the Win32 PDH.dll API, it takes a long time. A long time, I mean 3 seconds. I would run an app, and to get the first reading, it takes 3 seconds. And I thought, well, that's kind of weird. That's pretty slow. What's going on? So I did the same thing. I look at the DLLs, and I've noticed that when I try to read a counter, it loads up about 50 DLL, well, maybe not 50, but about 20 to 30 DLLs just to get a CPU counter. It pulls in the entire .NET framework, and it pulls in ASP.NET DLLs. This is to get the CPU counter in your machine, okay? If you don't believe me, and you have a Windows XP box, just attached to Task Manager and see what's going on. It's insane. So this is the types of complexity we talk about in Windows. It's not clear-cut. You know, on Unix, you know, you're going to be 5 libraries. They're going to do very specific things, and you're done. It works well. On Windows, it's going to end up with 250 DLLs, which hijack your APIs, you know, many times over, and you just don't know what's going on. Very complicated to do sandboxing properly in Windows. So there's a conclusion for the sandbox bit. The processes run in the sandbox. It runs from kernel mode, so you can't bypass it. The sandbox control access to all resources, from files to processes, everything. Everything is controlled. And they describe using policy files, which is just a list of rules for a particular application. So, besides sandboxing and memory protection, which is already pretty good, and you can't get this, you can't go to SourceForge.com and download this stuff. It's not there. Sandboxing plus ASLR already provides some significant advantages. But there are other things that you can do. The system protection layer was designed to harden the underlying operating system. Like I said, Windows is a very complicated beast. It can do a lot of things. But that functionality does not necessarily need to be there. So for example, your secretary probably doesn't need to debug applications, but you can. Okay? So you can disable a lot of the functionality without actually losing any of your features. So most of the people don't need to use features such as debugging or DOS16 emulation. You can disable functionality that's used by keyboard loggers, and most certainly your secretary won't be loading any kernel drivers, so you can disable that. And finally, the system protection layer also includes access to removable media. So we can control access to our media. So you can come up with a USB stick, you can stick it in, and you can configure that it's read-only, it's non-executable, whatever. It also comes under the hardening of the system. So here are some examples. I mean, this is some of the rules. So for example, protection debugging, turns on protection which disables debugging. So if you know that your company doesn't use debugging, you're not a software company, you can probably disable debugging and not lose anything. Similarly, why do you need DOS16 emulation on your machine? Unless you use debug.com or edit.exe, which you probably don't, you don't need it. Interestingly enough, if you remember, EI published a local ring 0 attack last year. This relied on some of the DOS16 emulation, on some of the LTD manipulation. Ozone was already developed by that time. I analyzed all the system calls in Windows, and I figured, well, who's going to be using this DOS16 emulation? It looks way too dodgy. And I was right. Several months later, I read an EI advisory, which is basically a ring 0 attack. But no one ever uses the DOS16 emulation, so you don't need it. You can disable it. The keyboard stuff will disable keyboard loggers, which use global hooks. You can also do things like you can disable time change, right? So if someone owns you, they can't change the times and logs and to roll it back and hide themselves. You can do that. The token modifier you can disable. This is basically to prevent attackers from escalating the local privileges. And as I mentioned, you can, for example, make your media so USB sticks read-only. So these are some of the examples of what you can do to lock down the system without actually losing any of the functionality. You will not notice any side effects. Some of the challenges include the fact that, once again, Windows is complicated. Don't be surprised if you find out that your Acrobat.exe actually loads kernel drivers. Don't be surprised at all. So there are some legitimate applications that require loading of kernel code drivers. I'm not even talking about system user processes which do this. I'm talking about normal applications which do funny stuff. So you can't simply say, don't allow the loading of kernel drivers, end of story, because you will break applications. So you have to be specific. You have to say, this process is not allowed, or this process is allowed only to load a specific kernel driver. So it's not that clear cut. Another thing is when you're locking down the system, let's say you created a rule which disallows write access to Windows System 32 directory. Well, which is great. I mean, you can't, people can't install, can't install rootkits or, modify your binaries. But the problem is you just killed your patching process, right? If you ever update your patches, which you should, then you've just broke that. So you can't say don't disallow all writes to Windows System 32 directory because you'll break things. Internet Explorer will load, it will download a bunch of binaries, you'll run them, and they'll overwrite your kernel files. And it's okay. It happens in Windows every week, every Tuesday, as a matter of fact. Your binaries get overwritten, and everyone goes on. So you have to be careful. You can't just lock down the system. Well, you can, but you'll break things. So you have to be careful about how you lock it down because there are some challenges. So, a quick summary, we lock down the underlying operating system by protecting the core resources, the core files, registry resources, and we also try to reduce the attack surface. This is the main point. We reduce the attack surface. We remove debugging, we remove DOS16 emulations, remove the stuff that can be exploited, but is not used in 99% of the machines. So, finally, before I give the demo, another important point is self-protection. If you saw the demo that I gave last year, some of the HIP systems that are on the market, they're not very secure. Not only I can bypass their buffer overflow protection, my shellcode can call netstop, hips.exe driver, and it will stop it. And it's okay, you can disable it. So if you don't protect itself, and you only protect the other stuff, let's say you missed some kind of attack and you get owned, if the next thing that happens, your system gets disabled and then it gets rootkitted, well, what good is that? So you have to protect itself. Ozone has to protect itself. So you can't, for example, the way it does this, it prevents everyone from disabling it. You can't stop the user-run service. You cannot disable, for example, you cannot stop the kernel driver. You simply cannot unload it, end of story. In addition, you can't load we try to prevent people from loading kernel code. Because if you can load kernel code, then you can just disable us from there. It's too simple. And as I mentioned, everything is reinforced in kernel mode. So it's hard for user policy to attack us directly because they're in user line, we're in kernel. So we're the master and they're the slave. So as a conclusion, as you all probably know, if you go down to Fry's and you buy your Windows XP and you go home and you plug into the DSL line and you go to Windows Update, you try to download the patches, by the time you're done downloading the patches, you're owned. It is that bad. A brand new laptop, if it's not patched, will get owned in probably under 10 minutes. And there are a lot of attacks out there. There are buffer overflows, there are local privilege escalations, there are nasty emails. There's all kind of stuff, all kind of stuff. So to address this huge issue, the Ozone was designed with security in depth in mind. So we took a bunch of attack vectors. I looked at them and said, well, how can we stop them? How can we prevent them? And Ozone tries to give you the tools which you can use to lock it down. Because today, to be honest with you, Windows security consists of putting your Windows box behind a firewall, running an antivirus and updating the signatures on it every 15 minutes, and patching every Tuesday. That's how people do security in Windows today. That's bad. That is really bad. If you go to any company, to any big enterprise, and you ask where the Windows machines are, they're hidden away. I don't know any single enterprise which allows, some enterprises disallow Windows machines in DMZ altogether. Others just firewall them off, don't allow any connection. So people don't trust Windows. And, you can understand that, until Windows 2003, Windows was Swiss cheese. It was really bad. If you go back a couple of years ago, Windows 2000 with IS5, you might as well just give out your admin password. Same thing. So Ozone consists of multiple layers which stop a variety of attack vectors. I talked about stopping memory-based attacks, which is based on randomizing the DLLs. I talked about locking down the processes by running them in a sandbox. I talked about hardening the underlying operating system without breaking anything, and also protecting itself. So are there any questions before I give the demo? Or should I give the demo and then do questions? Let's do the demo first. So let me show you. This is not Vapor Dream, honestly. And okay, here we go. So let's start with memory protection, okay? Let's start with memory protection. Let me show you what I'm talking about when I'm talking about randomizing. So I have a little program here which prints out which prints out addresses of a stack, heap, and a DLL. And if you run this program on a normal system, on a Windows system, it'll show you the same addresses. In fact, you can run it on different machines, on a different Windows machine, it'll get the same addresses across the entire enterprise. It is that similar. So let me disable the stack protection for this particular process to show you what I'm talking about. So the program is called stack.exe, and here is all the list of all the policies. And as I mentioned, it's just a text file which you can modify. And so what I'm going to do is I'm going to disable it. So I'm going to say protection is off. So we're not doing anything with this process. And I'm going to run it. So it's called stack.exe, and I modified stack.exe policy. So if you can see this, I mean, the main point, you don't need to concentrate on addresses, but the main point is, as I run it, the addresses are the same. It's going to be the same on this machine, and it's probably the same in your machine. Or if it's not the same, it's slightly different. Okay? So this is the same for every single machine on the internet. If I enable protection, that is, I enable the memory protection stuff, and I run it, again, the picture changes considerably. So if you look at the two instances here, once again, the address is not very important, but you've all of a sudden noticed the addresses are all over the place. You know, one instance is in, you know, at 100 megabytes, the other is at 200, the other is at 300. So they're all over the place. So this is what I'm talking about. So if you try to run an exploit, let me show you. I have a little exploit that I wrote. And it's basically all it does, it, you know, straight up mem copy, overwrites the return address, which then prints out the message box which is owned. The way this would work, let's see if I have the thing here. The program is called overflow, and if I tell turn all protection off, then you'll see that it's going to get owned. So let's turn off memory protection stuff and run the program. So overflow, you run it, and you get a little message box which says you're owned. And like I said, I overwrite the return address, and the return address points to a function which says you're owned. You know, in a real exploit, this would be pointing back into payload, which does things. Now, if I run it again, it'll work again. If I run it again, it'll work again. The reason for that is because addresses don't change. The thing here, if you look at this binary junk, this is a built-in address, and this address doesn't change. It's the same. It'll probably be the same in your system. So if I give you this program and you run it, you will get owned. Or rather, you know, you'll see the message to your own. Because it's the same. But if I enable the protection, if I say protection overflow is on, the address is not going to be the same anymore. It's going to be very, very different. And if I run it, well, nothing's going to happen. The reason for that is because the program basically goes away. It dies. Because the address that I overrode it with doesn't exist anymore. It just points into void. So Windows simply kills the process. And this is what I'm talking about. You're not owned, but your process probably went away. Most of the services will just restart, which is good, but it's also bad because you can be brute forced. But that's how it is today. So, you know, like I said, you know, this is the policy file. You can read it. You know, it's English. Oops. You can probably understand what it says. So let me show you some more specific policies. Let's say a command that exits the policy. So let's say you want to say you have a rule that says you can't access a file called 1234. Okay? If I open command and I try to do it, if I try to access the file, which is called 1234, it'll fail. It'll fail again and again. And there's no way I can bypass this because this is running from kernel len. And what you should also notice, I guess this is the important bit, is that I'm running as administrator. Okay, so I'm an admin on this box, but it still works. And the reason for this is because it's coming from user land. So I don't care who you are. You know, you're an admin in your system, whatever. The policy is being enforced on you anyway. So if you have IS, which runs with system privileges, it doesn't matter, it'll still work. So another policy, I mentioned there's a global policy which applies to all users and all commands. And let's live in computer.policy. And there, if you specify a rule, it'll apply to every single process, every single command you run, you'll do it. So for example, I have a rule that says time change deny, right? I mean, it's pretty clear I can't change the time. So if I now go and try to change the time as administrator, which you obviously can, it's not going to work. So if someone hacks and tries to change the time to roll back the logs, they won't be able to do it if you have this rule turned on. So I'm running as administrator, but it doesn't matter. So let's say I want to say it's, go back 2 minutes and clean the logs. So I say apply, and if you look at back here, it's still 0110. It silently fails it. You can't change the time. Let me share another example. For example, I have a rule which states you can't inject DLLs. Okay, you can't inject random DLLs into processes, which is being used, for example, it can be used by various exploits. So there was an exploit published a while ago, actually, and what it does is it injects a DLL into a system process, and then it steals your password hashes. Okay, password hash is supposed to be protected. You know, they're stored in a registry hive where you can't access it, but by injecting the DLL, you can bypass it. So if you try to run pwdump2, you should be able to get the hashes, which is equivalent to your passwords. So I have to make sure that, for example, the policy doesn't disallow. So VMware is a bit slow. So if I now run pwdump2, it's going to give me my password hashes. Well, there should be no other way for you to get them on Windows, except this way, right? So this is bad. This is like me stealing a password, more or less. And the way, like I said, the way this works is this program will inject a DLL into a system process and just dumps it off straight from there. Now, there is no need for anyone to eject the DLL in your system process, okay? It just doesn't happen. So as a rule, you would have a policy, a global computer policy, which says you cannot inject DLLs into your system process. Okay, so when you run the same thing as administrator, you get failed to open LSAS 5. 5 means access denied. So that's another example. So there are many, many, many different things you can do. But I guess I'll take the questions now. Yeah. Well, NT only works on Windows 2000 on XP and up at SysCenter. Yeah. So the question is, what type of performance do you have in Sandbox? The question is that the performance hit is quite minimal, right? What basically happens when you try to, let's say you're trying to copy a file somewhere. So what you do is you open a file, you get a handle, and then you copy it over. We only intercept, the only time Ozone interferes is when you open a file. Once you open your file, right, you can copy your megabytes and megabytes of data, and you never touch Ozone code. So you run at full speed. So the only initial performance hit is when you open the file. And that's pretty fast. And to open a file, it's performance overhead of, which it might be high, it might be like double what it would be to open a normal file. But if you look at the actual action of copying a file or reading a file, it's talking about like 2 or 3% of the over the overall life of that object. Right. I mean, FileMon, does it hook registry? System calls, because I thought it used filter drivers. But anyway, it's reasonable. Yeah. You can't, as a normal user, go straight to the ports because you're not allowed, right? So the direct port access would be disallowed in Ring 3, unless you have some IOPL stuff set up. So I don't protect against direct system port access, but Windows does, because if it didn't, it would be owned. So I actually don't need to do anything extra on that. Windows does good enough of a job for that particular piece. IOPL as a system? Probably. But I guess, well, it depends how you set up. I mean, you can't deny it to system as well. So it varies. Yes? So are you talking about the fragmentation of virtual address space? Well, the way I do it is all the initial DLLs are loaded straight up in linear fashion, the same way as Windows does, but at a different base, right? So if all your DLLs used to be loaded at the end of userland, and I randomize you to, let's say, to the first gigabyte, all of your DLLs, instead of getting loaded there, will get loaded at the first gigabyte in a linear fashion, so you don't get fragmentation as bad. Yes. It doesn't have to be that way, but yeah, it's in the same order at this point, so same way as Windows would do normally. Yes? Is it possible to get around the sandbox mechanism using COM objects? If you use in-proc COM objects, then the COM object is going to be loaded in the same address space, so you're going to be subject to the same sandbox rules. If you use out-of-proc COM objects, then it's potentially possible if we don't restrict that. So since most of it is in proc, it applies, you have the same problem, it applies the same way. So in proc COM, which is the majority of them, will be subject to the same sandbox mechanism. The way the allocations will work when you talk about probably create section is that they will, yeah, I think that gets randomized as well, because unless you of course specify that when you create a section, you can specify if you want to load a specific address. If you don't specify it, Windows will take whatever address. I think the address will get randomized as well. So, I'm sorry. Yeah, go ahead, please. Say it again? Do we hook open thread? When open process for sure. I can't remember open thread. Why? Say it again? Yeah, we try to prevent that stuff. Yeah. So for example, like pwtemp2, well, I mean that's process open, but it's very similar, right? Where you just try to inject stuff into your address space you're not supposed to. So, yeah. Yes? Say it again? Do we do anything against brute force? No. We don't protect against brute force attacks. I mean, it's possible to say, if your process is getting respawned 100,000 times in a minute, then stop it. But we don't do it. I mean, it's possible. But I think it should be done by like a separate processor or a separate module. I mean, I'm pretty sure your logs will get filled up pretty quickly as well. So we don't do it. I mean, it's possible. We haven't decided. Okay. Do you have 10 minutes? Okay, so more questions? Yeah. Yeah, that's a good question. As a matter of fact, when I said the question was, well, can't you, intercept some of those crashes? Yes, you can. When ASLR changes the address, that's one of the things I meant to do, but I didn't, is I want to look at when ASLR, when you have an exception, I can catch the exception for you and see where the exception landed, right? So if I see the exception is being landed in your kernel 32, or what was supposed to be kernel 32.dll, and I know it's not there anymore, that I can be pretty sure that's an exploit that uses static address, which means I can log the fact and kill the thread. So yeah, that's definitely possible. One of the things I want to do. Yeah, that's a good one. Yeah. The question was, is it feasible to add time-based policy? Or is it too much overhead? It's feasible. It's not done. Would it be too much overhead? No, it wouldn't. It would be almost no overhead whatsoever. So yeah, it's definitely feasible. I just haven't done it. But there's no overhead in doing that. Yeah. The ASR, what's my source of entropy? The system clock? No, I'm just kidding. I've looked at how the Windows kernel uses some C generation. They basically take, I take like all this performance counters, which are some crazy numbers. I take the actual system clock, but not the time, but the number of ticks that's got loaded. I take some thread and process ID, I mix it all up. This is pretty much how it was done by some Windows people as well for seeding. So it's pretty difficult. But, you know, nice try. Yes? How do I protect my policy files? That's a good question. I mean, you can say write access to your policy directory is forbidden, which means you can't modify them anymore, right? That's fine, you can do that, but means, well, if you need to change it, what do you do? Well, you need to reboot the box now, because as you remember, there's no way you can override the rules, okay? So you need to reboot the box in a safe mode and change it, so that's not very acceptable. So one of the things you can do is you can say, you can create a global policy rule which says denies access to all users. If you remember, there's multiple hierarchies. So you can create a computer global policy which says deny rule to the policy files except for a specific user, except for a specific application, except for a specific application running by a user. So you can create, you could say some weird user running Notepad is allowed to change that file, for example. So you can do that, or you can just deny them altogether, right? It's up to you to make that decision, because in some environments it might not be acceptable for change at all. So you actually need to reboot the box to do it. For others, of course, it's not very manageable. So you create, quote unquote, little loopholes which allow you to do that. But it's a very narrow process. A specific user, a specific process, doing a specific thing is allowed to modify a policy file and nothing else. You can do that as well, because obviously it's up to you to create the granularity. The question was, do I only do the file name? Well, it's the path name versus the hashes. Yeah, I haven't done the hash stuff. I mean, it's trivial to do. I haven't done it, but you can do it. You can do it on certificates. You can do it on hashes. I haven't done it, but I mean, it is very easy to do. It is very easy to do. How often are the policy files reread? Every time, right now, every time you start a process, it's reread. So if you modify the process, the policy, and you restart the process, it'll automatically pick it up. If you didn't modify it, it'll still reload it. I mean, you can add a timestamp. I just haven't done it. Because once again, overall, it's pretty cheap to parse a policy versus the create process, which is very, very expensive. Yes? What point the boot process is loaded? We load very early. When you do, there's a value in the driver which says when to load. The first one is 0, and 0 means at boot time. And at boot time, nothing has been created. I mean, I think only NTS kernel is loaded, and that's it. So that's one point. We load at the next point where some of the drivers were loaded, but I'm thinking bumping it up to where it's loaded even before anything is done, before a single driver is loaded, before anything. So it's NTOS kernel, and that's it. So we load before a single process created, before a single driver is loaded, before anything has happened. So we control the entire thing from the moment it boots up to the moment it's shut down. Yes?
Are you currently doing any checks on opening device physical memory?
So the question was, are we doing any checks on the device physical memory? Yeah, the question is yes. The question is yes, and I'll show you how it is. I mean, it's not a specific thing. I just created a rule and it does it, which is pretty cool. So the physical memory, if you do a search for physical memory in a global policy, I have it running here. Sectional, if name is equal device physical memory, then deny. You have to be careful with this though, because for some reason, I remember now. When I first enabled this, and this was the night before I was supposed to give a presentation, I rebooted my machine, it didn't boot up. Or it booted up and it gave me the access of, I was supposed to activate my Windows. So it basically wouldn't allow me to log in and force me to activate the user, to activate Windows. And I panicked, of course, it's midnight, I'm supposed to give the presentation next morning. I was wondering what was going on. The problem is what's going on is that WinLogon on Windows uses device physical memory to do some magic stuff to find out whether it's a legitimate copy. So if you're going to do the rule which says sectional name equal physical device memory, you have to be careful to make sure WinLogon still have access to physical memory, because otherwise you're hosed. So just be careful. Yeah. Very good question. The question is, what's the impact on the developer when the randomization is turned on? I learned it the hard way. I was like, wow. I was reverse engineering this. All legal before I started. I was reverse engineering this protection scheme, which was used by some program, and I've noticed it was loading DLLs at random addresses, and it was really difficult because I had to, you know, I was attaching it with soft dice, and all the addresses were all over the place, and I'm like, my God, they make it really hard because I had to calculate the offset, you know, calculate all the runtime. I was like, this is a really, you know, this is a bitch. And these guys are good. And then I'm like, hold on a second. I forgot to turn off my randomization rules, which made reverse engineering very, very difficult. So yes, if you're doing any debugging, you probably want to disable it because it'll make it very difficult. If you're reverse engineering something, you might want to disassemble it as well, because otherwise you get too much credit to people who implemented it, because they haven't done anything like that, which they could have, but they didn't. So yeah, you might want to disable that. Do you think the the protection vendor shipped their product with symbols? They weren't that bad, you know. Yeah, when you're debugging your own code, yeah, it's symbols. Yeah, it makes no difference because it does it at runtime, so you can load it at any time. But you know, sometimes it can screw with you, I suppose. Yes. Yeah, the question is, can we do resolve kernel links? Yeah, that's very important because obviously you can do lots of different stuff. There are no symbolic links as such in Windows. Well, there are, but people don't know about them. But you can do things like subst, right? If you ever use subst, you can create my F drive. You can say, see, Windows System 32 is my F drive. Okay, so if you only look at the path name without resolving the name, you'll be screwed because you say, well, F is not a Windows System 32, right? So what you actually do is you open the object, you start resolving, and the thing is there are multiple symbolic links in kernel space, so you have to do it over and over and over again until you actually get the name. So yeah, it's a bitch to do, but yeah, we do it in the end. Say it again? Says who? Yeah, I know that how you do it, right? But okay, the question was, you know, there's an SCM API in Windows which loads the DLL, the kernel drivers, amongst other things like services. Yes, we hook that as well. So that we hook multiple points because there are multiple ways of loading a driver, but that's one of them. So if you want to disable the ACM API, you can. How do you disable it? The SCM, when you load, it's the service.exe actually doesn't load kernel drivers. Or rather, when you do the SCM, well, I mean, if you can tell to service.exe only to load only known good kernel drivers, right? If you know if there's a specific kernel driver you need to load, you say it's okay to load this, but deny everything else. I don't know. I haven't looked at that. So basically, you're saying ACM API will load a kernel driver in the context of service.exe. Then in that case, I guess it's not as granular as doing it in a per process. It's kind of either you're allowed it to kernel driver or you're not. End of story. So that's the granularity that you get. Yeah. So system drivers, you enumerate them and say it's fine. And as a matter of fact, the service.exe, let me check. When you boot up a normal system, when you boot up Windows, it won't, service.exe, I don't believe loads any kernel drivers. The only kernel drivers loaded by SMSSS.exe, so service.exe. So I'm going to see if there are any kernel drivers loaded. If there are none, then I know you can boot up a Windows without service.exe. One sec. It'll come up and I'll tell you. So one more question while Notepad is opening. All right, I might as well finish answering your question before I answer your next question. Jamie. It's at system call level. But can you repeat your question? I'm not sure I got all of it. Correct. Correct. Yeah, I mean, we hook at multiple places, right? You can't hook network stuff in Windows. That's another thing. You can't hook network stack in Windows using system calls. There are no system calls. So there is no connect system call. Okay, the network architecture is completely different. So there are multiple things. There are multiple places where we hook. But for resources like files, it is at system call level. So to answer your question about the kernel drivers, if you look at the policy, service.exe does not load any kernel drivers in a normal boot up. You would say, no, it's not. You would say driver load, name equal, driver.blah.sys, then permit. The rest, driver load, deny. That's it. You're done. Does that answer your question? Okay. Well, come talk to me after. All right, last question.
Is your node cache so slow because of network space randomization?
Partially, yes. Partially, but of course it's running on VMware. There are some, this is running, the reason why it's running VMware, I'm running Ozone on this system as well. So for example, talking about Skype, see I've got Skype running here. And I've got soft ice on this machine as well. So I'm running this on this machine, and as you see, it's pretty snappy, right? I'm running some development funny stuff on that VMware box, so yeah, it's not that slow. All right, I believe that's all the time that I have. Thank you.